All right. Now, everybody in the room should have the same numbers for the concentrations in the data table for the lab. Which one is it again? We're talking H2O2 and Ki. All right. What is the concentration of H2O2 in experiment 1? Go ahead, Patrick.
0.14706.
That's about right. What about experiment 2?
0.294117.
Your numbers should be close, if not exactly the same. Okay. Experiment 3 should be the same as experiment 1. How about the concentration of I minus in experiment 1? Anybody?
0.025.
Nice. Experiment 2?
0.025.
And then experiment 3.
0.05.
All right. We are building one of those tables from chapter 14 where we examine what happens from experiment to experiment while keeping one thing the same. So our goal is to figure out N and M. N and M are the orders with respect to each individual reactant. Okay? So remember that our goal is to build a rate law. And raise that to whatever order each one is. Now, so far, we've seen these numbers to be perfect, right? We've seen 1s, 2s, 3s maybe at the most. That being said, we did this in an experiment. Are those numbers going to be whole numbers?
No.
Heck no. There's no way. A, there were so many sources of error that happened in this particular experiment. And B, we had issues just even understanding how to use the equipment at the beginning, right? So some of our results are going to be kind of skewed. I forgot the rate, didn't I? Oh, I put rate there. Oh. This is delta P over delta T. Okay? Each one of you should have values that put the change in pressure over the change in time in seconds on the bottom. So if you did not change your unit on the bottom to seconds, please make sure you go back and do that in your experiment. Okay? Who did I do this with yesterday? I did this with Gavin yesterday, right? Okay, Gavin, give me your delta P over delta T for the first one.
0.031.
And then the second one.
0.105.
And then the last one was 0.108.
Yes.
Okay. All right. Next thing to do is that that whole analysis of if this thing doubles while this thing stays the same, that means 2 to the n, which is the actual variable we're solving for, is going to equal whatever the change was in the rate. In order to figure this out, you're going to take the bigger of the two, divide it by the smaller of the two, and you're going to get a number. What was our number for this one?
1.77.
Well, that was n, right? Do you remember what the value was for the difference between the two? The reason I bring this up is because while I was working with Gavin in his lab data yesterday, we found a really convenient online tool to help you solve for weird exponents. Okay, and that's the thing that's posted underneath yesterday's daily Q. It says exponent solver. If you go to that link, you plug in this number, you plug in this number, and it gives you this number. So for him, we got this number to be 1.77 for the first one. Okay, that was what n ended up to be. Again, not going to be a perfect whole number, right? Going to be a weird number based on experimental error. Okay, do we understand how this happened? This one was 3.387. So we took this one, we divided it by this one to get the factor that this one increased by, set it equal to 2 to the n, solve for n. Again, use the exponent solver that's on your Canvas website. Super easy, perfect results. Yes, ma'am.
What's the difference between N and M?
N is the order with respect to H2O2. M is going to be the order with respect to I. So let's do I next. With I, we're looking for 2 experiments where H2O2 stayed the same, and all of you have this data the same, right? So all of you should use experiments 1 and 2 to figure out how H2O2 changes, and all of you should use experiments 1 and 3 to determine how I changes. From 1 to 3, I does what? Goes up by 2. So we're going to write 2 to the m equals whatever the change here is. So again, I'm going to do 0.108 over 0.031 for Gavin's data specifically.
3.5.
Thank you. So we're going to set 2 to the m equal to 3.5. And the solver kicked out 1.8. What did it kick out? 1.8?
We just put 1.80.
So now I have the full rate law to work with. Now I've got values for n, values for m, and now how do I solve for k given all of this information? Anybody remember how to solve for k?
Yeah. Plug it in.
Plug in one set of data, okay? So I'd use experiments 1, 2, or 3, you pick. You plug in all of the data, you have to do it for each one to find what k is for each and then average them. If you do this part right, these numbers are going to be very close. I think Gavin's had a swing of like 20. His was like 680, 700, and 680. Like his numbers came out exactly the way they should. If you do this part right, these numbers will come out right. Okay? Plug in your experimental data, and by that we mean what? Now that we have our rate law based on our n and our m, let's say we did the first one. Let's do experiment 1. The rate we calculated was 0.031. K is the unknown. Concentration of H2O2 is 0.14706. Ooh, the concentration of I minus is 0.025. I'm sorry, Olivia, I'm not ignoring you.
No, you're
Solve for K. And you're going to do it for each of the 3 experiments to find your K values, okay? I want you working on your lab data and finishing it up. You can work with your lab partner on it. Go for it. These 6 numbers should be exactly the same for every single person in the room.
Okay.
Because everyone did the same 3 flasks
Right.
of data.
But what about the ones
After that, that's experimentally determined. So this was delta P over delta T for each different one. And then this stuff is all stuff you have to take using your rate, just like we just did. More to come. So for the remainder of first period, because remember 2-period class, they're going to work on finishing up the lab data, which you should have access to, and then they're going to finish up their homework and get it submitted by 8:50. Okay? You guys need to make sure you do get it submitted, but the second video you see is going to be us going over the homework set, like the whole thing. Okay? All right, have a great day. I'll see you in a little bit.